race to win wars and explore the stars, have created some of the most fantastic products ever designed, and we use them every day, unaware of their amazing origins. On Wicked Inventions. Tracked vehicles from farm to war and tank back to tractor. Microwave oven, the cooking offshoot of World War II radar technology. Anesthetic machines, the culmination of the quest to find pain relief. We reveal the amazing science and manufacture behind these wicked inventions. One of the vehicles that revolutionized warfare in the 20th century was the tank. Mobile, rugged, and possessing immense firepower, the secret to the tank's effectiveness is the tracks on which they run. While the inventor of this ingenious continuous track system has been hotly debated, one of the first truly successful practical examples actually started life in the more sedate world of agriculture.
In Grantham, in the early 20th century, a firm called Hornsby invented the caterpillar track to make a tracked vehicle. In effect, what you have is a vehicle that runs on wheels, and you wrap the road around the wheels. So as the vehicle proceeds, it puts down its own road, goes across it, picks it up, and goes on laying it down in front.
The track's effectiveness was due to its ability to adapt to the terrain. The slack in the track allows it to conform to different features like rocks, with its tread gripping the surface, while the load of the vehicle is spread across a large area, preventing it getting bogged down. With machine gun fire and boggy terrain preventing effective troop movement on the Western Front, it is no wonder the British viewed a tracked vehicle as an answer to breaking the stalemate of the First World War.
A man called Ernest Swinton proposed that an armoured vehicle should be made with appropriate caterpillar tracks to get across the countryside. And the man who really took it up was Winston Churchill. He established a committee to examine the idea, and the first of the prototypes was built in Lincoln. It's called Little Willie, and you had this thumping great engine, this great big tin box. No one could really see out of it. You were looking out of a little slot trying to work out where you were. The guns were mounted on the side of it because the track went clean round the outside of the vehicle and you had nowhere to put a gun. Oh, it was a miserable thing, but it was very effective.
From these humble beginnings, tanks went on to dominate the battlefields of the 20th century, and the effectiveness of tracks has seen the system used continuously on a wide range of civilian vehicles. From farm to war, tank to tractor, continuous tracks are truly a wicked invention. The tracked vehicle has come a long way since their invention at the turn of the 20th century, and AGCO's Challenger MT765E is the latest type of tracked agricultural vehicle. When it entered production in 1986, the Challenger was the world's first rubber-tracked agricultural tractor and is now manufactured at AGCO's Jackson, Minnesota facility in the USA.
Track tractors are sold anywhere from Australia to Zimbabwe and from America to New Zealand, so they're all over the world. The biggest advantage to tracks is that it has a very wide, very long footprint. It has very little soil compaction, which affects your yields and your soil conditions year after year. One of the biggest benefits of a track tractor is you have a suspension built into the mobile track system. That really helps the ride quality of the operator. And people across the world have said that once you go to a track tractor, you'll never go back to wheels.
Building the Challenger requires multiple tasks and parts being assembled simultaneously and then brought together on the final assembly line to create a finished vehicle. This process can be broken down into three main assembly lines: the MTS or Mobile Track System, the cab, and the main line, where the parts are built off the powertrain and the MTS and cab are added when complete.
For the tractor assembly, we've been as high as 12 units a day, 2 shifts. But generally from the beginning to the end of the process to build the tractor, it takes about a week. And during that week, not every step is actually putting on parts. There's only about 2 days worth where we're actually putting on parts. And that'll happen in 17 workstations.
The main assembly line starts with the transmission being set onto an assembly cart that will help move the tractor through the assembly process. The Challenger transmission must be extremely robust and has 16 forward gears for greater power control. The transmission has now been attached to a sub-assembled frame. On this frame, a variety of hydraulic hoses and tubes needs to be installed in preparation for the engine to be married or joined to the unit. There will be 30 to 40 tubes per tractor, which will be connected to cooling and fuel systems, with 15 to 20 of them installed at this point. The monster 16.8-litre V12 engine is then installed.
End of 1986, the first Challenger rolled off the end of the line, and they made that tractor as the Challenger Model 65. That tractor was 265 engine horsepower. And to put this in perspective, as things have changed over the years, we don't even make a tractor that small anymore. That was a huge tractor at the time. Today, the tractors are up to over 600 horsepower.
Once the engine is installed, it is then time for the first quality check. There are 5 quality gates throughout the whole production process, where the work completed to that point is validated and reviewed. At Gate 1, the rear fenders are added, together with the cooling package, which is connected to the engine. The fill and filtration unit will be connected and the oil filtered throughout the hydraulic and transmission circuits. In addition, various other tests of the hydraulics are carried out, including starting the engine and various hydraulic circuits to test proper basic functionality. At the end of this process, the engine will be cooled, and all fluids will be drained from the systems. This unit then goes on to be prepped for painting. This involves the tractor being washed with water which has been purified using reverse osmosis, which removes many types of molecules and ions from the water, including bacteria. The tractor is masked prior to and also after the water cycle to protect certain components with cap plugs and plastic bags. The tractor is then painted with a high solid single coat paint. Once the fuel tank, radiators and air intake systems have been installed, the cab is set onto the chassis. The cab has been built separately and has already undergone electrical and heating system checks. Diesel, antifreeze, engine and transhydraulic fluids are added to the tractor. Then it undergoes a midline test where approximately 1,000 different tests are conducted to check the functionality of the different systems on board and to make sure all the parameters are correct. Once the quality inspection is passed, the hood is installed and then the MTS, or mobile track system, is connected.
Steel track machines have always been used in farming, but the thing with a steel track machine is it's slow. Rubber tires started to take over because they're fast, and a continuous rubber belt that's a track is the way to do it. We have a lot of weight to deal with. The track carcass is very, very thick. It is mostly steel cable inside it, even though everything that you see is rubber. Part of the reason why we have so much steel inside it is that we have to be able to take a lot of track tension. We use friction drive, and friction drive you might say, oh, everything's going to slip inside of it. That's not really the case, because all you have to do is have enough track tension, and you can drive through dirt, you can drive through mud. Water, no problem.
Once the tracks have been connected and aligned, the vehicle has to finally pass the jounce, or shake test. During the test, the tractor is literally rocked and shaken in order to simulate road and field operations. This test will reveal any leaks or other potential problems at the factory, meaning that any issues can be resolved well before the finished tractor is delivered to the customer. This test is the very last step in the production of a Challenger tractor, and once passed, the tractor is ready to be put to work. The microwave is a familiar sight in most people's kitchens throughout the world. With its ability to rapidly heat food, it is everyone's choice for cooking the snatched after-work ready meal or knocking up a speedy bowl of porridge in the morning. But this fantastic culinary marvel was actually born out of World War II radar technology. During World War II, the Allies perfected a piece of equipment called a cavity magnetron. The magnetron generated high-powered microwaves which could be used in compact radar sets that could detect much smaller objects and with smaller antennas than the radar that had previously been used. At the end of the war, a team led by the self-taught engineer Percy Spencer began experimenting with this wartime radar technology to understand what industrial applications it could be used for, and by chance stumbled upon an interesting characteristic of the electromagnetic waves produced by the magnetron.
There were some engineers working for a Raytheon company on a piece of radar equipment, and one of the leading scientists suddenly noticed the chocolate bar in his pocket was melting, and he couldn't quite understand it. And then he did further experiments and realised it was the microwaves from the radar set which he was working on, which was then causing this to melt. And he then set up some further experiments just on this. And very quickly, people realised that it was a very, very efficient way of heating food of almost any description.
Spencer's employers, Raytheon, were quick to see microwave's potential and unleashed the first oven onto an unsuspecting world in 1947. Standing at nearly 6 foot high, weighing a hefty 340 kilograms, and retailing at an eye-watering $20,000 in today's money, it was aimed squarely at the catering industry. But by the late 1960s, smaller and cheaper microwave ovens started to appear in domestic homes, and by 1975, microwave ovens were outselling their gas-powered cousins. So, how do these awesome ovens actually work?
A microwave works by producing radio waves in a small environment in order to heat your food. We think of radio waves as what you hear on the radio itself, but what a radio wave is actually is a form of energy that is transmitted. So in a microwave you have a coiled wire that is heated, electrons are stripped off that, and then spun around in the presence of a magnet. In doing so you produce radio waves, and what we do is we produce radio waves at a very specific frequency, and that's the one that heats water. As most food contains a large amount of water, these radio waves go into the food, heat up the water molecules, and in doing so that transmits the heat to the rest of the food. What's special about radio waves is that metal will essentially stop them. So your microwave is actually contained in a container of metal, and that reflects the radio waves back to the food.
Microwaves are not just used for heating food. Your mobile phone also uses microwaves to communicate to transmission towers, but as these are of a low intensity, they will not actually start to cook you. And microwaves are still used in modern radar systems. We are exposed to a full range of radars, including police speed control, weather and air traffic control radars that have little impact on the human body. But one type of military radar reminds us of the dangerous power that radio waves can produce.
Radar and the radar emissions at particular frequencies, certainly close up, are very, very dangerous. One specific type of radar is called a fire control radar, or to target a ship or an aircraft. And these are very, very powerful. Instead of a beam which is quite all round to give an overall picture, they're very localised, almost like a pencil beam, to lock up an aircraft. Clearly the power which goes through them and with the frequency means they are pretty dangerous. Certainly I know of one episode when a quick trial was taken with a particularly high power fire control radar, when somebody actually had a loaf of bread and dropped above the radar and just dropped it down. So the time it took to go through the beam, by the time it landed, it was toast. It was just burnt. It was that strong.
Reheating leftovers, but developed from war-winning radar, the microwave oven is truly a wicked invention. Microwave ovens may have revolutionized our kitchens, but we're going to show you how to create a piece of the sun inside these cracking cookers using nothing more than a grape. What you will need: some grapes, a knife, some tissue paper or kitchen roll, and our trusty microwave oven. To begin, take a grape and carefully cut it in half, leaving an isthmus, or small piece of skin that connects the two halves. Next, get rid of excess moisture on the grape halves by patting the fruit with a tissue or kitchen towel. The reason? More on that later. Now, place the grape into the centre of your microwave and shut the door. As we are dealing with awesomely fantastic cosmic forces, please be advised to shield your eyes, and as this experiment can damage your microwave, don't try this at home. Our intrepid tester turns the microwave on to full power for 10 to 15 seconds. And behold, the sun appearing inside the oven. Did you see the flaming cloud erupting from the grape? This is a material called plasma, and is known as the fourth state of matter, following on from the other states which are solid, liquid, and gas. So, what is it? Well, plasma is a cloud of protons, neutrons, and electrons, where so much energy has been added that all the electrons become energized, to the point where they become loose from their respective molecules and atoms. On Earth, this makes plasma useful, and we see it used in plasma torches which cut metal, and inside colourful neon signs. But the biggest and best example is our very own sun, whose heat rips off electrons from helium and hydrogen, creating a big plasma ball. But how does it work? When you cut a grape in half, but leave a skin flap connecting the two halves, the result is more or less the right length for it to act as an antenna, which concentrates the full power of the electric fields inside a microwave. These are electromagnetic waves that cause electric current to move back and forth between the two halves of the grape. This current is concentrated in the piece of skin between the two, which will heat up to the point where it bursts into flame, and has absorbed enough energy to briefly turn into a plasma cloud before it dies. And the grape drying? The water in the superheated grape turns to steam that can hinder the creation of the flame, so patting the fruit with paper minimises the amount of steam present in the reaction. So, there you have it, a little piece of the sun created inside a microwave oven. Alleviating the pain of the wounded soldier has gone hand in hand with easing the experience of a civilian undergoing the surgeon's knife. Until the 19th century, the best a patient or wounded man could hope for was their pain to be eased by drinking alcohol, a solution that was not in the best interests of them or their surgeon.
So as you can imagine, in the early days of anaesthetics, it was quite traumatic for the patient to have to see them actually have, for instance, their leg being amputated. Also for the surgeon, it would be a problem because not only would the patient be moving and struggling, but also they would have to perform the operation quite quickly, perhaps without not much technique, just to try and get the procedure done in a timely manner. This could lead to a lot of blood loss and perhaps a suboptimum procedure being done.
Although herbal sedatives based on plants like the opium poppy had been used by the ancient Chinese and Mesopotamians for thousands of years, in 19th century Europe and America, other potential anaesthetics such as ether and chloroform were being experimented with. With the first successful public demonstration of pain relief due to ether administration in 1846, these substances seemed to offer the answer to pain-free surgery. But with their use came risks. Patient deaths started to mount up as the varying dosages required was not understood, and overdoses and long-term illnesses resulted from their use.
With the things like ether and chloroform, it was quite hard to get the doses right for each individual patient. Everybody's very different in their size and also their body mass, and that may be a difference between muscle and fat distribution, which will distribute drugs differently within the body. So chloroform was invented later to ether, and it was a more potent agent, and so it was very effective. However, it did have some major side effects. Especially in the anxious person, it could lead to sudden death, and later on, if not used in the correct doses, it could lead to liver damage.
Beginning at the turn of the 20th century, better anaesthetics and procedures were developed, which has resulted in today's pain relief coming a long way from the few shots of brandy taken to dull the effects of an amputation. In the modern operating theatre, anaesthetic machines are used to help sedate patients, and Penlon, based in Oxfordshire in the UK, are one of the leading manufacturers of this medical technology. As with all Penlon devices, the modern-day anaesthetic machines begin life in research and development, where a team of designers, engineers and programmers hone the designs and ensure compliance with international standards for safety, accuracy and ease of use.
Obviously an anaesthetic machine is going to be used in theatre on a patient, so it's life critical that it's correct. So the standards are very tight, tolerance is very tight, and that ensures the machine is reliable and performs to the correct specification.
More than 850 individual components are used to create an anaesthetic machine. Some of these are made on site, while others are commissioned from specialist component manufacturers. These are the needle valves and filler blocks, which are important parts of the vaporizer. The main assembly is where the machine starts to take shape, starting with the trolley that will house the equipment. Wheels, legs and drawers are attached to the frame. The gas blocks, pipeline assembly, back bar and electrical panel are attached before the unit is piped up and tested. With such a crucial medical device, there are many rounds of testing. The flow meter is fitted and checked, and the operative checks the gas blocks for possible leaks. While the trolleys are being made, another line assembles the ventilator. The chassis is put together. The control and regulatory blocks, along with the ventilator screen, are assembled and the units are enclosed. Another line builds the vaporizers, which are one of the key parts of the anesthetic machine. They convert the liquid anesthetic to a gas state and add controlled amounts of the gas anesthetic to the oxygen that is flowing through the machine. Because gases' properties vary at different temperatures, it is important that the temperature is constant, so compensators are fitted to regulate the temperature of the gases. Now, the valve lock is being assembled. As the vaporizing unit is prepared for calibration and the precise pieces are fitted together, it starts to take shape. The calibration and dial assembly are vitally important, ensuring that only the precise level of anesthetic required is administered.
Pre-calibration, we fill the vaporizer up with agent because it needs to be calibrated with agent in the vaporizer. We then sit the vaporizers for 2 hours to climatise. They then go into the test room where they're calibrated using laser refractometers.
These components go through rigorous quality control checks, with gases being passed through the devices and the results being scrutinised. After testing, the vaporizers are drained and dried, so no residual liquids are left inside. Then the filler block is assembled. Another important element of the anesthetic machine is the absorber, which removes the carbon dioxide from the system. The absorber is assembled with heaters, and the electrical boxes are added and tested. The absorber and ventilator are tested. Displays and monitors are added before further tests. When all the extensive checks have been completed, the anesthetic machines are shipped out to hospitals in more than 100 countries across the world.
To build a typical spec anesthetic machine, including A200 absorber and ventilator, would take approximately 24 man-hours if one person were to start from beginning to completion. On top of that, we also would have approximately 8 hours test time for a complete system.
Enabling doctors to perform life-saving and life-changing surgery, anesthetic machines are truly a wicked invention. So there you have it, a dash through the hidden history, super science and amazing manufacture of products that you use every day, but have never realised their amazing background. Tracked vehicles, microwave ovens and anesthetic machines, all wicked inventions.